Swayam Prabha. Digital India. Educated India.
Hello and welcome back. So right now we are discussing about recrystallization, which is nothing but formation of strain-free grains in a deformed metal. And in the previous lecture, we have discussed about the mechanisms of nucleation of strain-free grains. So we are going to continue on that in this particular lecture. So now that the nucleus of the strain-free grains has formed, it has to grow, right? So this recrystallization process also is a nucleation and growth kind of process. So this nucleus now which has formed is strain free, but rest of the material is still strained. So this has to grow and consume the rest of the strained material for it to be recrystallized, right? So this nucleus has to now grow, and the growth in this case occurs by grain boundary migration, so that it can consume the rest of the strand material, the rest of the strand grains. In order to explain this phenomena as to how exactly the grains grow when the nucleus with a particular size which is greater than the critical size forms, as to how exactly it can grow during this recrystallization process, that can be understood by a similar phenomena, but much simpler compared to what can happen in a metal which is being heated. If you consider the soap bubbles and look at how they grow, in a given time interval. Okay, so here if you look at the soap bubbles carefully, they also look like grains, right? The bubbles which form in a froth, for example, they can be considered similar to grains because there also you have boundaries between them, and those boundaries have their own energy. Okay, so there is an interfacial energy which is involved, and across the boundary this energy is different, right? Because you have different size of bubbles, their surface energy is different, the pressure difference is also there between any two bubbles, right? So considering all these factors, it can be taken as an analogous system like grain and grain boundaries what you have in metals. Okay, so if you form the bubbles and then let them grow and observe it in a given time interval, and after every few seconds, or after a particular time interval, if you capture the images, you could actually visualize how these grains are growing, okay, in terms of the growth of these bubbles, right? So what happens is you would have grains of different orientations and also different morphologies in terms of how many sides they can have. Okay, so you can have a grain like this, right? You can also have a grain like this with sides less than this one, and you can also have another grain like this, right? So their shape and their size could be different. Okay, now if you look at the growth of these bubbles as a function of time, you would find that this kind of grains having different number of sides will form, and the ones which are having less than 6 sides will be actually unstable. So these are the grains which will tend to dissolve. So in this case, this will be those bubbles which will disappear, and the ones which are having 6 or more sides will grow at the expense of these unstable grains, right? And if you notice carefully, you would see before disappearing, they would actually come down to a shape which is having only 3 sides, because this is the most unstable shape in a system like this where you have grains and grain boundaries. Okay, so if you look at the ones which are disappearing, you would find that before disappearing, somewhere a triangular grain like this one will form. Okay, and now if you see in the next stage, after a certain time interval, you would see this grain has disappeared. Okay, so before disappearing, they will turn into a triangular geometry, because what happens in this case, now if I just simply magnify this region, this small triangular grain that you have, it will be somewhat like this, and it will try and maintain an angle of 120 degree between these boundaries. Okay, and in order to maintain this angle, they will be actually curved like this, which is concave towards the center, right? So because of that curvature, this will tend to move towards the center. And shrink as a result of that movement of these walls or these boundaries towards the center, and ultimately disappear. Okay, so that is how the rest of the grains around it will grow at the expense of this one. Okay, and following a similar logic as to how the boundaries move, you can also understand why the grains having more number of sides will not shrink, or rather grow. Okay, so if you have a grain like this, with 6 or more sides, this will be concave away from the center. Okay, or it is with regard to the center, it is actually convex, right? So therefore, the movement of such boundaries will be towards this direction and not towards the center of the grain, right? And as a result of this grain will grow. Okay, and this growth, of course, is temperature dependent. And what will be the final grain size after the recrystallization process, that will also depend on the recrystallization temperature, as we would have discussed before also. So this is just to understand as to how the grains grow and why some of the grains are favorable for the growth with respect to the others. Okay, Now, there is one more mechanism which is proposed to throw some light as to what exactly happens and how the grains grow, and that is through a coalescence kind of process by simple geometrical coalescence, where two grains can merge into one bigger grain. Right, so let's say you have these two grains like this, and they are separated by these small grains over here. Okay, A and B are separated by C. So when these two grains approach each other, A and B, C has to shrink, right? So that will be something like this if you just look at as to how these two grains can approach. Right, so this is how these two grains can approach to each other. And as that happens, there are two possibilities with regard to the boundary that separates these two grains. Okay, so it is quite obvious from here that A and B are more favorable for growth compared to C, because you can see the number of sides for C is much lower compared to A and B. So C is going to shrink and A and B are going to grow, right? As you could see from here also. So ultimately this smaller grain C will disappear and there will be a boundary developed between these two grains A and B. Okay. So with regard to that boundary, there are two possibilities. One, it can be a boundary which is close to high angle. Okay, let's say this boundary. And they can also approach in a manner where the misorientation across this boundary will be very low. So this is close to high angle misorientation. That means this is the misorientation across this is more than 15 degree. But there is a possibility that it will be a low angle kind of boundary or a subgrain boundary kind of boundary where the misorientation across it is much lower. So the difference in terms of the orientation across this boundary is much low. So this boundary is going to actually disappear, and these two grains A and B will now merge into one bigger grain. So this is how, as the boundary develops, depending on the character of the boundary, these two grains can coalesce into one bigger grain, and that is how they will grow in size. So these are the different ways of looking at the grain growth phenomena which occurs after the grains are recrystallized. Okay. And as we have discussed before, the grain size basically depends on, of course, the temperature and also the degree of deformation. So for any given material, if you plot the recrystallized grain size against the percent deformation, which could be, let's say, percent elongation, if you have deformed in tension, for example. So as the degree of deformation increases, the grain size will be finer. And one more thing that you can notice over here is the fact that you need a minimum amount of deformation which is needed for the recrystallization to occur. Okay, so this is the critical amount of cold work which is required for the recrystallization to occur. Okay, so this is what is known as the primary recrystallization. Which occurs by nucleation and growth. But now, once these recrystallized grains have formed, if you continue to heat the material or hold it for longer time, then what is going to happen? So there is still enough driving force for the boundaries to move and the grains to grow, because it will still try to reduce the surface energy in an effort to reduce the energy of the system, right? So that can only occur when the number of grains would reduce and the grain boundary area would decrease. Okay, so this is the driving force for the grain growth to occur. And if you keep on hitting the material or keep on holding it at a particular temperature for a longer duration, then due to this driving force, there will be a tendency for the grains to grow further. Okay, so if you let this happen, in fact, there could be a situation where the grains can grow abnormally, okay, beyond a particular time. So here we are talking about a scenario where all the grains are already recrystallized, right? Grains are all strain free, and we still continue to hold it And as I said, if you do that, the grains will further grow and it can go to a very large extent, the rate of growth, and it might lead to a phenomenon called abnormal grain growth. And this also goes by the name secondary recrystallization. Right? So if you want to reduce the abnormal grain growth, if you want to avoid the abnormal grain growth, you will have to define your recrystallization time and temperature accordingly. Okay. And with regard to the recrystallization temperature, you should also note that the recrystallization temperature is not really a fixed temperature like melting point, because as we have seen, it depends on other factors also, such as the degree of deformation and the recrystallization time, etc. And therefore this is not a fixed temperature. But will this be undefined or is it something arbitrary? It is not really arbitrary, because for a particular material you still may have a particular recrystallization temperature. So if you want to define the recrystallization temperature, it can be defined as follows. It is the temperature at which a particular metal with a particular amount of cold deformation will completely recrystallize in a finite amount of time, okay, which is typically around 1 hour. Okay, so that is how you can define the recrystallization temperature. Right? So what exactly will be this temperature? As I said, that will also depend on certain other factor, particularly the amount of cold deformation which is given to it prior to the recrystallization. Okay. And with regard to the progress of the recrystallization process, if you want to monitor how the recrystallization process progresses, then that can also be demonstrated, or can be seen experimentally when you take a number of samples having same amount of cold deformation and heat them at a particular temperature for different period of times. Okay, and after every time interval, you can cool down the material, you cool the metal, and then you characterize it, to see the microstructure, and from that you can actually determine what is the extent of recrystallization, or what percent of recrystallization has been completed in that particular time. Okay, so if you do so, you can generate a plot like this between the percent recrystallization and time. And this typically generates a S-shaped curve like this at a particular temperature for a particular material. Okay, and from here also you can again see the effect of the recrystallization temperature. If you do this at different temperature, you take the same material, deform it to the same level, and then you heat it to different temperatures and hold it for different amount of time. Okay, so as you increase the temperature, you would find that the time for a particular amount of recrystallization will also decrease, okay, as you increase the temperature. So if I take three temperatures, let's say T1, T2 and T3, T3 is greater than T2, greater than T1, right? So from here you can see that for a given amount of given percent of recrystallization, as you increase the temperature, the time needed decreases. So the effect of temperature and time can be shown by such plots. The effect of temperature on the recrystallization time can also be shown by an alternative plot. If we consider this fraction as 50%, the fraction corresponding to this horizontal line, if we consider that 50%, we will get the time required for recrystallization of half of the structure. Okay, so if we call that time interval as tau and plot it against the reciprocal of the temperature, we will get a plot like this, where the y-axis is the reciprocal of the absolute temperature, and x-axis is the time for half recrystallization. That is tau. Okay, so this will give rise to a straight line like this, which can be expressed by an equation like this, where k is the slope of this line and c is the intercept. And both of these are constants. It can be also expressed by an alternative equation of this form, where 1 by tau is the rate at which 50% of the structure is recrystallized. R is the gas constant, and Q is known as the activation energy for recrystallization. right? So through such plots also the effect of temperature can be seen. So from here you could see that as the temperature is increased, the time required for 50% recrystallization decreases. Okay, and this tau can be for any fraction. It doesn't have to be 50% all the time. It could be any fraction of the recrystallization, and from that you could see the effect of temperature as to what is the time required for a particular fraction of recrystallization at a particular temperature. And with that, we come to the end of this lecture. Thank you for your attention.